The author and conservationist Mark Shand once wrote, "People are so difficult. Give me an elephant any day."
Welcome to the A&P Professor, a few minutes to focus on teaching human anatomy and physiology with host Kevin Patton.
In this episode, I have an update in how memories are formed, and I discuss elephants in the A&P course. I'm going to start off this episode with a question, and I think you knew this question was coming. A couple of episodes ago, I assigned some homework, and so I'm asking you, did you do your homework? I reminded you about it in the last episode, and I don't think all of you did it. I know some of you did, but maybe some of you forgot. So I'm reminding you again, please do your homework, which is to tell at least one other person about this podcast. Just let them know something you learned in there or something you like about it or whatever. And you can do it by phone or in person or by email or text or Twitter or snail mail or whatever. And just let them know about this podcast. I really would appreciate it. And last time I gave you some additional homework, and I want to remind you about that. And that is to send me your questions, comments, advice, stories, whatever, regarding making accommodations for students with special needs, such as hearing or vision challenges, autism spectrum issues, or any of the many other challenges that we need to address in our A&P course. Because I'm going to have a future episode on that topic, and I sure would like to get some feedback, input, contributions from you before I start putting that episode together. Some research published recently in Cell Reports seems to add another clue in the puzzle of how exactly memories are stored in the brain. We know that the hippocampus is an important area of the brain for storing memories when we learn something, such as, say, what carbaminohemoglobin is. As you may recall, I love saying that word, carbaminohemoglobin. And I say it at every opportunity, this being one of them. So clearly my hippocampus has stored that memory, even if there's not much else stored there. We also know, or think we know, that memories are stored by way of long-term potentiation of synapses. That is, the signals at synapses involved with a memory are strengthened or made to work more efficiently. This apparently happens by recruiting additional numbers and types of postsynaptic receptors, some reorganization of the cytoskeleton in the postsynaptic cell, and some changes in adhesion between the cells involved in the synapse. Well, this new research seems to show that a protein called Netrin has a role in all this that we hadn't noticed before now, at least not operating this directly in long-term potentiation or memory formation. We already knew that Netrin plays a role in forming new synapses, which is important in brain development and learning. Now we know that when certain postsynaptic receptors are triggered, a subtype of a glutamate receptor, they induce the secretion of Netrin from postsynaptic cells, which in turn changes function at the synapse by triggering the formation of additional numbers of another subtype of postsynaptic glutamate receptor. So the postsynaptic neuron now has more glutamate receptors, and its sensitivity is now cranked up a notch. That is, we've achieved long-term potentiation. Or put simply, we formed a memory. So what's new here is that we have a protein, Netrin that seems to be a key molecule in the process of learning and memory. And what that means is, A, we're getting closer to fully understanding human memory, and B, we now have some potential drug targets for improving memory-dependent functions in general, but also specifically in neurodegenerative disorders such as Alzheimer's disease, Parkinson's disease, amyotrophic lateral sclerosis, ALS, and other disorders. So what does that mean for me and my A&P course? Well, I can't see myself diving too deeply into this in my class. I already feel like I'm frying the brains of my students by trying to get them to understand just the basic mechanics of synaptic transmission. But I do mention that receptor subtypes exist, for example, the alpha and beta adrenergic receptors. And we discussed the concept of learning and memory is related to making synapses more efficient. Because all that partly answers the question, why do we need to know any of this synapse stuff anyway? And while talking about learning and memory, we'll probably discuss how scientists have recently discovered that the protein Netrin is released at some synapses to strengthen them by increasing the postsynaptic receptors. And additional activation of the synapse means even more Netrin, which means even more receptors and an even stronger memory. So that mantra for learning that I coach them in, which is practice, 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 at some levels kind of boils down to Netrin, Netrin, Netrin. But I won't ask them to explain that on a test. On the test, I think I'm just going to focus on the core concepts of synaptic structure and function. If you want to know more about which receptors are involved and some more details of the proposed mechanism, check out the links I have for you in the show notes and the episode page at theapprofessor.org. And I also have one of my sloppy little diagrams there that you're welcome to use. The A&P Professor podcast is sponsored by the Human Anatomy and Physiology Society, HAPS, promoting excellence in the teaching of human anatomy and physiology for over 30 years. Go visit them at theapprofessor.org/HAPS. I love elephants. If you know me, or if you listen to the preview for this episode, you know that I've worked with elephants in zoos and circuses. I've been a part of Elephant Society. I have a good friend who's an elephant, which is an amazing experience, as you can imagine. So when I run across new scientific discoveries involving elephants, I pay attention. Just like I pay attention when I run across stories about carbaminohemoglobin. There, I got to say it again. Carbaminohemoglobin. I love saying that word. Okay, getting back to elephants. There were a few elephant updates recently that got me thinking that I've never mentioned to y'all how elephant biology plays a role in my A&P course. Depending on your own background, you probably bring things into your course that apply to A&P concepts to liven things up a little bit, while at the same time using analogies to make things more easily understood. Well, I bring elephants to class. Well, not literally. Although, I did do my dissertation defense on a circus lot in between performances with that elephant friend I was talking about. There's a picture of the two of us in the show notes and episode page at theapprofessor.org if you're interested. By the way, for any of you facing a future dissertation defense, I strongly recommend providing your committee with cotton candy. It creates the cheerful, festive mood we all want for our dissertation defense, right? Anyway, there were several interesting elephant updates in the literature in the last few months, and I'm not going to go into all of them. But I'll mention a few, and you can click on the links if you want to follow up on them. For example, elephants are famous for their memory, a topic I just brought up earlier in this episode. And some research confirms the complexity and reliability of that memory in being able to discern very subtle differences among humans they encounter. Now, any of us who've worked around elephants could have confirmed this, but it's nice to have scientific data to document it. And then there was the recent story about how elephants have evolved a variant of a normal mammalian gene that can become active when cancer cells appear, and then that triggers apoptosis, possibly explaining the very low incidence of cancer among elephants. And there was the study on elephant tails that proved that, yes, those tails do move fast enough to flick a pesky mosquito and even create a thin current of air over and around the elephant's body to further discourage flying, biting insects. But the one that really got me thinking about elephants in A&P was an update regarding elephant skin. This is usually where I first bring up elephants in my A&P course, when we talk about skin. Why? Because besides having to deal with insect pests, elephants have a huge problem with dissipating heat from their massive muscular bodies. And like humans, they use their skin as a major part of how to solve that problem and maintain homeostasis of body temperature, thus using the skin as a thermoregulatory organ. But since they don't produce either sweat or sebum, how does this work? Well, the new research explains the mechanism behind one of the ways that the skin of African elephants helps dissipate heat by increasing the skin's surface area. If you've ever seen an African elephant, or even just a picture of one, they often look like they're covered with huge splotches of dried mud. And often they are. The mud can have a cooling effect through evaporation as the mud dries, and the dried mud can act as a bit of shade from the rays of the sun. And besides, the mud helps with those pesky insects, right? But even after you give your elephant a bath, which is always fun, no, really, it is fun. Even after she's mud and dust free, her skin will still look like it's caked in mud. That's because on many parts of the elephant's body, the stratum corneum builds up a really, really thick keratinized layer rather than sloughing off to form the thinner layer of keratinized tissue that we see in humans. I mean, it does eventually slough off, but just not so soon. So it gets really thick and it starts cracking. Well, those cracks are important. They do at least two things. One is that they increase the total surface area, which is good for getting rid of heat. And the surface area inside all those cracks all over the back and sides of the elephant really adds up. Another thing the cracks do is they help the mud adhere to the skin. So that new research I just mentioned explores the mechanism behind the skin cracking caused by what you would call hyperkeratinization of the skin. And it kind of shows that African elephant skin, which you already know is very wrinkly, is this amazingly complex fractal-like surface. That is a surface that has bumps that in turn each have their own bumps, that have bumps, that have bumps, that have bumps, and so on, producing an almost infinitely large surface area. So, yay for efficient thermoregulation, right? Before you ask, and I know you're thinking this, you're wondering how itchy it must be for African elephants. Do African elephants feel itchy in those overly keratinized areas of their skin? Well, I don't know. You'd have to ask an elephant. But I'm certain they'd tell you yes, and that's because they act like it itches. When I worked at the zoo, they rubbed up on the walls of their night stalls a lot, scratching those itches. There were elephant-colored stains on the wall. But that's exactly what happens in the wild, too. I've seen African elephants in national parks and reserves scooting up against big trees to scratch their itch. I remember one spot where some huge fallen trees seemed to have been polished because it was a popular local spot for elephants to come and have a good rub. When I worked in the circus, we'd do special events that sometimes involved going into a building. Well, that is, if the building had large enough doors and strong enough floors. And I'd have to be very careful to keep Flora, my elephant friend, away from the walls. Turns out that textured walls are especially attractive surfaces to rub on. And a set of shelves, wow, that must be heaven for an elephant to scratch on. On the circus lot, trucks and trailers were in danger from elephants for this reason. To this day, I can't look at a rearview mirror on a big truck in a parking lot without thinking it was no wonder that elephants thought they'd make good back scratchers. So clearly, the keratinization of elephant skin is partly regulated by regular self-grooming, which is what all that scratching is. In zoos, circuses, and sanctuaries, it's keepers who must perform a lot of this grooming. I used one of those stiff wire brushes sold for scraping paint. Flora loved that. But the problem is she'd lean into it when I was brushing her. So it was kind of dicey business. Anyway, humans do a bit of this too, right? I mean, take, for example, those big loofah sponges or those sanding tools intended to grind down the sole of your foot. By the way, elephants also have thick skin on the bottom of their feet, just like we do, except a bit thicker. If we humans lived out in nature, the thick skin on the bottom of our soles would be scraped a bit with each step on rough ground, and we'd never think of using one of those foot sander thingies. We'd probably not need to trim our toenails either. Well, elephants are the same way. In zoos, circuses, and sanctuaries, they need regular foot care, which means they have to be taught to give their keepers their foot on command and let the keeper give them a pedicure. Once they get the hang of it, they seem to really like it. I guess it's like spa day. I think a major part of it is that they like the attention of their keeper friends. Sort of like my dog loves his ears rubbed. But I think they like how nice their feet feel afterward, too. Unlike humans, elephants walk on their toes. Well, not entirely. When you look at the bottom of their feet, it looks flat, with the toes along the anterior perimeter of a rough circular footpad. That footpad is covered in thick skin. Deep to that is the hypodermis, as you'd expect. But the hypodermis here is really, really thick, filling in the space between the flat skin of the sole and the tarsal and metatarsal bones. In other words, it's like the style of shoe called a wedge. But instead of a solid supporting wedge between the sole of the shoe and the foot, it's a big blob of adipose tissue. So it's sort of like a squishy wedge that forms a natural cushion. If I were an elephant, I'd want that. I use this to explain how the adipose tissue of skin can act as a support and a cushion at the same time. I tell my students it's just like they're sitting on their adipose as they're listening to my elephant story. In my A&P class, the integumentary system is the first system we cover. And as exciting as I try to make a survey of epidermal strata and the many functions of the hypodermis, it can be kind of overwhelming. But adding an elephant story or two can sure liven things up a bit, and at the same time teach something about the stratum corneum and the process of keratinization and the functions of that hypodermis. But wait, there's more. African elephants have those big giant ears. It turns out those are mostly for thermoregulation, not for hearing. I mean, really, they're mostly flat. Not exactly the best shape for funneling sound waves, right? Actually, elephants have pretty good hearing. I could talk to Flora with music blaring and crowds roaring, and she'd hear me perfectly. Although now that I hear myself say that, I wonder if it wasn't mind reading and not good hearing. Did I mention I think elephants can read minds? Wait for the research to confirm it, of course, but remember, you heard it here first. But getting back to those big flat ears, they make wonderful thermoregulatory extensions of the skin. They have moderately thickly keratinized skin on the anterior surface, but the posterior surface is very thin. Not only that, there's a very extensive network of blood vessels there, very close to the surface of that very thin skin. Those ears must weigh a ton with all of the blood in them. So yeah, I'd say those are pretty efficient radiators. But it's even better than that. The elephant can easily adjust the amount of heat lost through their ears. I always tell my students to watch an elephant's ear when they go to the zoo or watch a National Geographic special. If the elephant's ears are mostly close up against their head, then it's probably not feeling particularly hot. But as they feel a bit warm or a little bit overheated, they'll hold their ears a little ways out from their head. thus allowing more convection across that thin, blood-perfused posterior surface. I'm sure the volume of blood flowing through the ear changes too. I'm pretty sure of that because as an elephant gets hotter and they hold their ears out perpendicularly, it's easy to see that the veins are more dilated than usual, evidence of more blood flow at that moment. When an elephant starts waving its ears back and forth, then that really gets the breezes going and helps even more with dissipating heat. You probably want to retreat to a safe distance, not because the elephant might get a bit crabby when it's overheated. I know I get that way when I'm overheated. But the other reason an elephant may start flapping its ears is to scare you away because it feels threatened, or that you're an intolerably stupid person for approaching it without a proper introduction and is about to stomp on you or do a headstand on you. See, I'm teaching you some life-saving skills in this episode. Don't walk up to an elephant unless you've been properly introduced, and certainly get away from an elephant that starts flapping its ears at you. If the ear flapping isn't enough to cool the elephant, and there's some water around, the elephant may suck some water up into their trunk and spray it behind their ears. The water evaporates just like sweat would on a human skin, and it adds to the cooling effect. Remember, elephants don't sweat. Thank goodness. I love elephants, and I love spending all day with elephants, but I'm not sure I'd feel the same way spending all day with a sweaty elephant. But as we can see, they have other ways to get evaporation going besides sweat. Oh, wait. There's one more thing a very hot elephant can do. If there's no water around, they can spit into their trunk and spray that behind their ears. Even so, I'd still take that over a sweaty elephant. So besides giving some examples in humans of how we can make use of changes in blood perfusion of the skin and the phenomena of conduction, convection, radiation, and evaporation from skin to maintain our set point body temperature, I can describe some really odd and really memorable adaptations of elephant skin, including the elephant's ears. Even if you don't have any elephant friends of your own, you can still use elephant stories in your teaching, right? And all those other things that are part of your life that you can bring in as analogies and entertaining asides while you're telling the story of human structure and function. I have more elephant stories, practically for every system of the body. If you want to hear more, you got to tell me. Or if you want me to shut up about elephants, tell me that too. Or anything else you want to tell me, maybe even a cool story that you use in teaching. Just call the podcast hotline at 1-833-546-6336. That's 1-833-LION-DEN. Or send me a message or sound file at podcast@theapprofessor.org. A searchable transcript and a captioned audiogram of this episode are funded by AAA, the American Association of Anatomists, at anatomy.org.
The A&P Professor is hosted by Kevin Patton, professor, blogger, and textbook author in human anatomy and physiology.
No animals were harmed during the making of this episode.